You know that feeling, right? You walk outside on a really hot, humid day, and the air just feels thick, sticky.
Oh, yeah, almost heavy.
Or, you see the condensation dripping down a cold glass, and you wonder, what's actually going on there scientifically?
It's something we all experience. And behind those feelings, there's quite a bit of science dictating our comfort. It's pretty fascinating.
Absolutely. So today, we're diving deep into what are called gas-vapor mixtures. We're really going to focus on the air we breathe, the everyday air, and all that water vapor hiding inside it.
Hmm.
Our goal here is to give you a kind of shortcut, a way to really grasp these key ideas: atmospheric air, humidity, how air conditioning actually works.
And why it all matters, not just for your comfort, but even for big industrial stuff.
Exactly. We'll unpack some maybe surprising facts, connect the dots. Hopefully by the end, you'll feel genuinely well informed about these invisible forces shaping how you feel every day.
Sounds good. So where should we start? Maybe just the air itself,
Yeah.
because it's definitely more complex than just thinking of it as a simple gas, especially with water involved.
Yeah, I think most people, myself included initially, just think air is a gas.
Yeah.
But the sources we looked at kept using the word vapor. What's the difference? Is it a big deal?
It is, actually. It's a subtle but really crucial distinction. When we say vapor, we mean a gas that's pretty close to becoming a liquid. It's near its saturation point.
Okay.
So condensation is a real possibility, like steam or your bathroom mirror fogging up.
Right.
Regular gases, like, say, nitrogen, way above its boiling point, they usually stay well above their critical temperatures. Condensation isn't typically on the table, but air mixed with water vapor is different. That water part can easily condense out, and that changes everything.
Which leads us to the air we actually breathe.
Mm-hmm.
We hear dry air, atmospheric air.
Yeah.
What's the story there? Are they interchangeable?
No, not really. Dry air is more of a theoretical concept.
Yeah.
It's air with absolutely zero water vapor, purely hypothetical in the real world. Ah, okay.
Atmospheric air is what we're actually surrounded by. It always has some moisture, some water vapor in it. The basic gases in dry air are pretty constant, but that water vapor component, it's changing all the time. Depends on weather, location, oceans, rain, even us breathing.
So even though water vapor is just a small fraction of the total air,
It has a huge impact, really punches above its weight, you could say.
in terms of how we feel, our
What?
comfort.
Absolutely. Human comfort. And it's fundamental for designing and running any air conditioning system. You have to account for it.
Okay, and here's something that jumped out at me from the material, maybe technical but important. Even with all this complexity vapor, potential condensation for the temperature range we usually care about in air conditioning, say roughly -10 to 50 Celsius, or maybe 15 to 120 Fahrenheit. We can apparently treat both the dry air and the water vapor as ideal gases. And the air is tiny, like less than 0.2%.
That's right. It's a hugely convenient simplification for engineers. It makes the math manageable. So we don't need super complex equations for everyday AC calculations.
Exactly. For dry air, we just use a standard value for its heat capacity, its Kp. And for water vapor, its energy content, the enthalpy. We can approximate it pretty well just based on temperature alone. There are simple formulas for that. It works remarkably well in that range.
Okay, so we have dry air and water vapor mixed together. How do their pressures work? Do they interfere with each other?
Nope, they just add up. Simple as that. Dalton's law, right? The total pressure of the atmospheric air is just the partial pressure of the dry air plus the partial pressure of the water vapor.
We call that water vapor pressure, just
Vapor pressure.
often, yes. So say the total pressure outside is 95 kilopascals. If the water vapor is exerting 2 kPa, then the dry air must be exerting the other 93 kPa. They each occupy the whole volume, but contribute their own pressure to the total.
Got it. Okay, that makes sense. So let's actually quantify this moisture now. How much is really in there? I know there are different humidity terms. Let's start with specific humidity. What's
Ooh.
that? Right, specific humidity, usually written as omega. This is the absolute measure. It's simply the mass of water vapor present divided by the mass of dry air. So kilograms of water per kilogram of dry air, for instance.
Okay, the actual amount of water stuff per amount of air stuff.
Exactly. And related to this is the idea of saturated air. That's air holding the absolute maximum amount of water vapor it possibly can at that specific temperature and pressure. Any more water added, it just condenses out as liquid.
It's full. Can't hold anymore.
Precisely. And there's a handy formula engineers use to calculate specific humidity, relating it to that vapor pressure we just talked about and the total pressure. It lets them pin down that exact amount. O equals 0.622 times PV over P minus PV.
Right, the technical bit. But then there's the one we hear about all the time, relative humidity. That feels more connected to comfort.
It absolutely is. Relative humidity, often phi, is the one most people experience directly. It's a ratio. It compares the actual amount of moisture in the air to the maximum amount the air could hold at that very same temperature.
So it's like, how full is the air compared to its total capacity right now?
Perfect analogy. It goes from 0% for totally dry air up to 100% for saturated air.
And here's the kicker, the thing that explains so much, especially in winter, right? Relative humidity changes with temperature, even if the actual amount of water vapor doesn't change.
That's the crucial insight. Yes.
Yeah.
If you take some air with a certain amount of water vapor, a constant specific humidity, and you heat it up, its capacity to hold water increases dramatically.
Ah.
So even though the amount of water is the same, the relative humidity plummets. That's why indoor air feels so dry in winter when the heating is on. You're not removing water, you're just making the air capable of holding much more, so it feels relatively empty.
That makes your skin dry and everything crackle with static electricity.
That's the reason. Conversely, cooling air increases its relative humidity, pushing it closer to saturation.
Okay. And you mentioned enthalpy before the energy. Does that account for both air and water?
Yes, the total enthalpy of atmospheric air includes the energy of the dry air and the energy of the water vapor it contains. And critically, it's usually expressed per unit mass of dry air. That's essential for engineers doing energy balance calculations for heating or cooling systems. Got to know how much energy you need to add or remove.
Right. So we know the components, we know how to measure the moisture. Now, how do we decode the feel? You mentioned dew point and wet bulb temperatures earlier. Let's tackle dew point first. The condensation trigger, you called it.
Yeah, I think that captures it well. The dew point temperature, TDP, is simply the temperature you'd have to cool the air down to at constant pressure for condensation to just start forming.
So it's the point where the air becomes saturated with the water it currently has.
Exactly. Cool it any further, and water has to drop out as liquid.
And this explains everyday things, like dew on the lawn.
Perfect example. Overnight, the ground cools, the air near it cools. Its capacity to hold moisture drops. Eventually, it hits the temperature where its current moisture level is its capacity, that's the dew point, and further cooling forces due to form.
And my cold drink's sweating.
Same idea. If the surface of your can or glass is colder than the dew point temperature of the air around it, moisture from the air will condense onto the cold surface.
And fogged up windows inside during winter.
You got it. If the inside surface of your window pane gets cold enough, colder than the dew point of your indoor air, you'll get condensation. So if your room is, say, 20 degrees C and 75% relative humidity, the dew point is about 15.4 degrees C away. Your window glass needs to stay warmer than that to stay clear.
Okay, dew point is the when of condensation. What about this wet bulb temperature? TWB. Sounds a bit more practical, measurement-based.
It is very practical. There's a theoretical process called adiabatic saturation. Imagine blowing unsaturated air through a long insulated channel filled with water. The air picks up moisture and cools down until it leaves saturated at a certain temperature. That exit temperature is the adiabatic saturation temperature.
Okay, but how do we measure that easily?
Well, the practical way is the wet bulb temperature. You take a regular thermometer, but you cover the bulb with a wet wick, like a cotton sock soaked in water. Then you force air to blow over it, usually by swinging it around or using a fan.
And why does the temperature drop?
Because the water evaporates from the wick. And evaporation takes energy-latent heat. It pulls that heat from the thermometer bulb and the surrounding air, cooling the thermometer down.
So it reads lower than a regular dry bulb thermometer.
Yes, unless the air is already 100% saturated. If the air is saturated, no more water can evaporate, so the wet bulb temperature will be the same as the dry bulb temperature. And here's the really useful part. For air-water vapor mixtures near atmospheric pressure, the wet bulb temperature you measure is very nearly equal to that theoretical adiabatic saturation temperature.
Ah, so it's a practical stand-in.
Exactly. It makes it super useful. You often see devices called sling psychrometers, basically just a dry bulb and a wet bulb thermometer mounted together that you swing around to get a reading. Very common measurement.
Wow, okay. That's a lot of temperatures and humidities and pressures to juggle. Specific.
Pretty much. You can find the specific humidity, the enthalpy, energy, the wet bulb temperature, the dew point temperature, even the specific volume, all from that one point. It shows how everything is interconnected.
Okay, so how do you read one? What are the main features?
Well, typically, the horizontal axis is the dry bulb temperature, just regular air temperature. The vertical axis is specific humidity, the actual moisture content.
Got it.
Then you have lines all over it. There's a prominent curved line, usually on the top or left. That's the saturation line, where relative humidity is 100%.
Okay.
Then there are curves inside that for constant relative humidity, like 50%, 60%, etc. There are also lines for constant wet bulb temperature. These usually run diagonally down from the saturation line. And interestingly, they are almost parallel to lines of constant enthalpy.
No.
And there are lines for constant specific volume, too.
And you mentioned something interesting
Mm-hmm.
for saturated air on that 100% line.
Right. On the saturation line, the dry bulb, wet bulb, and dew point temperatures are all the same. They all converge at saturation.
That's neat. So if I know it's, say, 35 degrees C and 40% relative humidity.
You find 35 degrees C on the bottom axis go up to intersect the 40% RH curve. That's your point. From there, you can read straight across to the vertical axis to get specific humidity, follow the diagonal lines to find wet bulb temp and enthalpy, move horizontally left to the saturation curve to find the dew point. It's all there.
That is powerful. And you said it helps visualize processes, too, like simple heating.
Exactly. It's not just for finding static properties. If you just heat air without changing its moisture content, the specific humidity stays constant. So on the chart, that process is just a horizontal line moving to the right. Cooling is a horizontal line to the left. It helps you see what's happening to the air.
Okay, this chart sounds essential, which leads us nicely into the actual air conditioning processes themselves, mastering our microclimate, you could say.
Yeah.
The ultimate goal is human comfort, right?
Mm.
But it's not just temperature.
Definitely not. Comfort is really about our bodies being able to effectively get rid of the waste heat we constantly generate. Even sitting still, we're like little furnaces.
We have to dissipate that heat.
Yes. And the three main environmental factors influencing that are dry bulb temperature. Sure, most people feel good somewhere between, say, 22 and 27 degrees Celsius, maybe 72 to 80 Fahrenheit. Second is relative humidity. Generally, 40 to 60% is preferred. And third is air motion. We need a little bit of air movement, maybe around 15 meters per minute to help carry heat away, but not so much that it feels drafty.
And how does our body actually lose heat?
Yeah.
You mentioned sensible and latent.
Right. Sensible heat is what you'd measure with a thermometer, heat lost through convection, air movement over skin, and radiation, heat radiating to cooler surfaces. Latent heat is the heat lost through evaporation, primarily sweating.
Ah, so humidity affects the evaporation part.
Hugely. High relative humidity makes it much harder for sweat to evaporate. The air is already holding a lot of water, so it can't easily accept more. That slows down your body's evaporative cooling mechanism.
Making you feel hot and sticky.
Exactly. That muggy feeling is your body struggling to cool itself by evaporation. Low humidity, on the other hand, speeds up evaporation, sometimes too much, leading to dryness. And yeah, other things matter too, like radiation standing near a cold window makes you feel colder even if the air temp is okay, and wind chill from air motion.
Okay, let's break down some common AC processes using this knowledge. Simple heating and cooling first, where moisture is constant.
Right, so specific humidity doesn't change, as we saw in the chart. It's a horizontal line. Heat the air, you move right. Cool it, you move left.
And the key point about heating.
Heating decreases relative humidity. Warmer air can hold more moisture, so the existing amount represents a smaller percentage of the maximum possible. This is the winter dryness problem we talked about, dry skin, static shocks.
Makes sense. And simple cooling.
Cooling increases relative humidity, pushing the air closer to saturation.
So if just heating makes it too dry, the logical next step is heating with humidification.
Precisely. You need to add moisture back in. You typically heat the air first, then add water. You could inject steam, which adds both heat and moisture.
Or spray water.
Or spray water, but spraying water causes evaporative cooling, remember? So it actually cools the air down a bit as it adds humidity. You'd need to account for that, maybe heat the air a bit hotter initially.
Okay, now the opposite problem. Cooling, but ending up too damp. Cooling with dehumidification. Essential for places like, well, Florida in August.
Absolutely. If just cooling the air makes the relative humidity uncomfortably high, you have to actively remove moisture.
How's that done?
You cool the air below its dew point temperature.
Ah, the condensation trigger.
Exactly. As the air temperature drops below the dew point, the excess water vapor has nowhere to go but to condense into liquid water on the cold cooling coils. This condensed water is then drained away. The air leaving the coils is cooler and has a lower specific humidity. It's drier. It's usually saturated right at the coil temperature, though.
Got it. Okay, what about swamp coolers? Evaporative cooling. You mentioned they're good in dry climates.
Yes, very effective and energy efficient where the air is hot but dry. Places like Arizona, Nevada.
How they work again?
They work on that principle of evaporative cooling. Water is evaporated into the incoming hot, dry air. As the water evaporates, it absorbs latent heat from the air, significantly cooling the air down.
But it adds humidity.
It does. So you trade lower temperature for higher humidity. That's why it only works well where the starting humidity is low. In a humid climate, it wouldn't cool much and would just make things feel swampier.
Like the desert traveler wrapping wet cloth around their head.
Exactly the same principle. Using evaporation to draw heat away, you can get significant cooling, like taking 120 degrees F, 10% RH air down to maybe the mid-70s Fahrenheit. On the psychrometric chart, this process follows a line of almost constant wet bulb temperature and enthalpy.
Interesting. Okay, moving beyond treating just one airstream. What about mixing air? Like in big buildings?
Very common. Large buildings, hospitals, etc. often mix fresh outside air with recirculated indoor air that's already been conditioned. This is done for ventilation and energy saving.
How does that work on the chart? If I mix stream A and stream B,
If you mix them adiabatically, no external heat gain or loss, the state of the resulting mixture lies on the straight line connecting the states of stream A and stream B on the psychrometric chart.
a straight line between them.
Yep. And the exact position on the line depends on the mass flow rates of the two streams being mixed.
Now, here's a potentially weird one. Can you mix two streams that are not saturated and end up with condensation?
You absolutely can. It seems counterintuitive, but yes.
Oh.
Imagine the two initial states on the chart are, say, fairly humid but not saturated. If you draw that straight line connecting them, it's possible for part of that line to actually pass through the saturated region to the left of the 100% RH curve. If the mixing ratio puts the final mixture state in that region, then fog or condensation will form during the mixing. It's something engineers have to watch out for.
Wow. Okay, one last big topic. Those huge cooling towers near power plants. Wet cooling towers. What's their job?
Their main job is rejecting massive amounts of waste heat into the atmosphere. Think about a power plant. It generates a lot of heat that needs to be removed from its spin cycle, usually via a condenser.
And they can't always just dump hot water into a river, right?
Exactly. Water might be scarce, or regulations might prevent thermal pollution. So these towers provide an alternative. Warm water from the plant is sprayed down inside the tower. Air is drawn up through the falling water.
And evaporation does the cooling.
Yes, a small fraction of the water evaporates. This evaporation absorbs a huge amount of latent heat, cooling the rest of the water significantly. This cooled water is then collected at the bottom and sent back to the plant. The air leaving the top of the tower is much warmer and packed with the evaporated moisture.
And I've seen different shapes. Some look like huge chimneys, maybe hyperbolic. Others have big fans.
Right. The ones with fans are called forced draft towers. The fans actively pull or push air through. The really tall, iconic ones are natural draft towers. They work like chimneys.
Oh.
The warm, moist air inside the tall chimney is less dense, lighter than the cooler, drier ambient air outside. This density difference creates natural buoyancy, causing the warm air to rise and drawing fresh, cooler air in at the bottom. No fans needed, but they have to be very tall.
And the hyperbolic shape, is that for airflow?
Surprisingly, no. That shape is primarily for structural strength and stability. It allows them to build these massive concrete structures efficiently to get the necessary height for the natural draft to work well. It's an engineering choice for strength, not really thermodynamics.
Huh. And these are better than older methods?
Generally, yes. Things like cooling ponds or spray ponds require vast amounts of land area to get the same cooling effect. Towers are much more compact, though they do have their own costs and impacts.
Okay, wow. We've covered a lot, from why your drink sweats to these enormous industrial structures. It really brings home how concepts like vapor pressure, humidity, dew point, they aren't just abstract science.
Not at all. They directly impact how comfortable we feel every single day, and they're fundamental to the massive engineering systems that manage our climate, both indoors and even on an industrial scale for power generation.
Understanding this stuff, it feels like it gives you more insight, doesn't it? Not just appreciating your AC, but thinking about energy use, maybe even future building designs.
It really does. It connects physics and thermodynamics directly to our lived experience and to major technological systems.
So maybe a final thought to leave our listeners with. As we get better and better at understanding and manipulating these properties of air and water vapor, What kind of innovations might we see next in controlling our personal climates or tackling bigger energy and environmental challenges?
That's a great question. Smarter buildings, more efficient systems, maybe even ways to harness some of these natural processes more effectively. Lots to think about.